Let's pick up where we left off on multiple linear regression. We're now on to inference in the multiple linear regression model. The model for statistical inference here is similar to the single equation. The coefficients of a multiple regression model, the B0, 1 through P, are estimates of population parameters in the model. Y is equal to beta naught plus beta 1 x1 plus so on till beta p xp plus epsilon for error, where epsilon is normally distributed. Normally, we test slope parameters to see if they are different from 0. The test setup looks like a null hypothesis of beta k equal to 0, meaning that xk and y are not associated, and an alternative of beta k not equal to 0, which means that the xk and y are associated. The t-test statistic has degrees of freedom equal to n minus p minus 1, where n is the number of cases, p is the number of predictors in the variable or in the model. And we use the similar t-test that we've seen before, and we can find a confidence interval in the same way we have before. That's how we would test the individual regressors. Now, if we were concerned about the overall fit of the model and whether or not the model predicts better than chance, we use an F-statistic. And in that case, it's that all of the variables are equal to 0, and that's our null hypothesis, and our alternative is that at least one of them is not 0. And if there's sufficient evidence to reject the null, if the p-value of the F-statistic is smaller than or equal to alpha. And the good news is, if you're doing all this, the software will generate this statistic for you. I should note that this is not the only use of an F-statistic with linear regression, but it's a common use. Recall we were trying to estimate the relationship between education and this test outcome. We have our estimates, we have our standard errors for the estimates, t-values for the t-tests we just talked about, the p-values for those t-tests so that we can see what kind of significance each of those variables have, the r-squared so we can know what kind of variation or what proportion of the variation that we are explaining with our model, and finally the F-statistic and its p-value. Based on this p-value, we can know that we can reject the null hypothesis and say that at least one variable is not 0 to about any alpha that you might choose. So let's look at this again. We thought age might be a confounding variable, and we were concerned about statin use, and we were also concerned about cardiovascular disease. Again, the right way to do this is to know that you care about all these things and test them at once, and not to add variables in search of r-squared. We have the results here. Let's start with statin user. The estimate is 4.69. And that would mean that the presence or the respondent being a statin user would indicate that we should expect an answer or a score 4.69 points higher than non-statin users. And we can go ahead and slide across and see that we have a p-value of 0.05. And we can note that if we go just to the right of that, there's a period. And if you look at the significance codes below, the period indicates an alpha of 0.1. So it is significant at a level of alpha equals 0.1. Age is our next variable down. We see that each year we would expect a decline of 0.92029 points. And if we look on across here, we see that it is highly significant at a level of alpha equals 0.001. Then we go down again to education lower second. We see that that is 10.08. So we would expect a test score 10 points higher than the education baseline. And it's quite significant as well. It is alpha equal to 0.01. Moving down one variable, education higher second. Again, that's 21 points higher than the baseline education level. And it is highly significant at alpha equals 0.001. Education university is 33 points higher than the baseline education. And again, highly significant at the 0.001 level. Last variable, CVD, it's a cardiovascular disease presence. That would indicate that the person has a disease. And we would expect that one with the disease would have a score 7.5 or so points less than those without cardiovascular disease. And that is significant at the alpha equals 0.05 level. Our multiple and adjusted R squares measures both increased. The penalty for the additional variables is minimal, so they probably all are somewhat important. And by the multiple R square, we are explaining about 44% of the variation in the score. That still isn't great. It's better. But if we look at our F statistic on a line below that, it's 63.38 with a p-value of 2.2 to the -16th. And that's highly significant. So that's going to be alpha equals 0.001 level of significance. So the model is definitely showing some association between these variables and our test score. I would still caution the analyst that these could still be confounding variables, but we're getting closer. What if you thought that maybe age interacts with some of these variables or something to that effect? How would you deal with that? So one of the key assumptions of this regression model is that when one of the predictors, xj, is changed by 1 unit, then the values of other variables remain constant, that the predicted response changes by beta j, regardless of the values of other variables. But like I said, I mean, it's possible that two variables interact with each other, two explanatory variables interact. And we have such the effect that one of the explanatory variables, xj, depends on the value of one or more other variables. At its simplest, you might have one that is categorical and one that is numerical, and that's what we're going to do in this class. So consider a linear model that predicts total cholesterol level from age and diabetes status. Here we have this, and we have our expectation of total cholesterol is equal to beta naught plus beta 1 times age plus beta 2 diabetes. We can run that model and find that our intercept is 4.8, our age coefficient is 0.00749, and our diabetes is -0.3. Now here's our plot. This is kind of tough to see, and I'm wondering if it really is that there should be a downward slope on the red line. But just having the slope variable and then the dummy variable for diabetes does not give us the option of changing the slope variable for those with diabetes. And if you separate out the plots, we can see that, yeah, there is something to that. So we have a problem with our fundamental assumptions. We have one variable where the response depends on another variable, which means we don't have a fully specified model if we don't do something about it. So let's find a way to modify the slope variable. And we can do that if we change the model from expectation of total cholesterol is equal to beta naught plus beta 1 age plus beta 2 diabetes plus beta 3 diabetes times age. The beta 3 only matters if there is diabetes. Otherwise, it's diabetes 0, then that beta 3 times 0. So this adjusts the slope to deal with the differences that we saw in those plots. Now we see a little more reasonable result. We have our intercept, so our mean of all at 4.695. We have our age, so the cholesterol is going to go up by 0.0096 by each year, and diabetes is going to indicate if yes, then there will be a higher mean for cholesterol. So our intercept is shifting here. And then we can take into account the fact that that downward slope that we observed when we interact age and diabetes. And we have a slope change of negative 0.03. This is showing what I was talking about with the interaction only mattering whenever age or whenever the person has diabetes. As you can see here, the age times 0 on the bottom there, we see that 0.034 doesn't even come into play when we're calculating total cholesterol hat. And we see that it does come into play whenever there is diabetes. The significance of the interaction term, well, it's kind of the same as the others. And in this case, in this model, we're seeing that all of them are significant to at least the 0.05 level. And the interaction variable is significant to the 0.01 level. If that interaction variable was not significant, then that would probably mean that there's not enough evidence to show that there is an interaction. So you don't really need to have that term, probably. So I've mentioned a few times that chasing R square is not how you choose your model. There's some debate to this, but in general, that's true. But of course, there are exceptions. But in general, you want to have the most parsimonious model possible, which explains variation in the response using as few predictors as possible. You want to include all of the things that you think matter, but as few as you can. And maybe the chasing R square thing is just in economics. Maybe that we're the only ones that don't let you do that. But in general, you want to explore the variables, do those things, do an initial model fitting, but try to find out what you have that really matters, and then assess your model using residual plots, because you might have problems with your data that are correctable if you know they're there.